So let's look at a limiting reagent problem. A fuel mixture used in the early days of rocketry consists of two liquids, hydrazine and dinitrogen tetroxide. These ignite on contact to form nitrogen gas and water vapor. We want to know the grams of nitrogen gas that could be formed from 100 grams of hydrazine and 200 grams of dinitrogen tetroxide. In order to figure out the amount of grams of nitrogen gas, we have to know the limiting reactant and the excess reactant. We have to identify both of those, and that's going to require us going from the mass of hydrazine or dinitrogen tetroxide to the moles of each one of these, and then looking at the balanced chemical reaction to find out the stoichiometric relationship, right, the mole ratio of each one of these reactants to nitrogen gas. And we can see which one is the limiting reactant. And then once we've found the limiting reactant, then we can determine how much nitrogen gas is produced. And then we can also calculate the amount of excess reactant that remain unreacted once the reaction has gone to completion. So the first thing to do is to write a balanced chemical equation. So that's where we're going to start. So if you have hydrazine is a liquid, it tells you in the problem. It reacts with dinitrogen tetroxide, also a liquid, to produce nitrogen gas and water vapor. Water vapor is a gas. Okay, so we need to balance this equation. So the place I'm going to start to balance this is I'm going to start with oxygen. Okay, there's 4 oxygens on the left-hand side, but there's only 1 on the right-hand side. So if I put a coefficient 4 in front of the water on the product side, then we have the same number of oxygen on each side. Now I'm going to look at hydrogen. On the product side, we have 8 hydrogens, so we need 8 on the reactant side. In order to achieve that, we can put a 2 in front of hydrazine. So now we have to deal with nitrogen. On the left-hand side, we have 4, 5, 6. We have 6 nitrogens. So on the right-hand side, we need 6, but we only have 2. So we can put a coefficient 3 in front of this nitrogen gas. So now we have a balanced chemical equation. And so what we want to do is we want to find the moles of nitrogen gas produced from the mass of both hydrazine and dinitrogen tetroxide. This will allow us to ID the limiting reactant. Okay, so I'm going to shrink this and let's find the moles of N2 from hydrazine first. Okay, we have 100 grams of hydrazine. We can find the moles of hydrazine using the molar mass. For every 1 mole of hydrazine, there are 32.05 grams. And then we can use the relationship of moles between hydrazine and N2. So for every 1 mole, sorry, for every 2 moles of hydrazine, that's just the coefficient from the balanced reaction, there are 3 moles of N2. And then once you punch this in your calculator, you get 4.68 moles of N2. So this tells us from 100 grams of hydrogen, it is possible to produce 4.68 moles of nitrogen gas. All right. So now I'm going to calculate the moles of N2 from dinitrogen tetroxide. So we have 200 grams of dinitrogen tetroxide. Well, you can use the molar mass to find the number of moles of dinitrogen tetroxide. The molar mass for this is 92.02 grams for every 1 mole. And then from the balanced chemical reaction, I know that for every 1 mole of N2O4, there's 3 moles of N2. My grams cancel out, my moles cancel out. So from this we get 6.51 moles of N2. Okay, so the limiting reactant is the one that produces the smallest amount of moles, right? And so that one is the hydrazine. So hydrazine is our limiting reactant. So limiting reactant. So we're going to use that to calculate the amount of grams that we can produce. And this is our theoretical yield. So if we have 4.68 moles of nitrogen gas, we can look up the molecular weight of nitrogen gas. It's 28.02 grams N2 for every 1 mole of N2. And moles cancel out. We have 131 grams of N2. So that's how much can theoretically be produced. So we're not finished yet though. We want to know how much leftover dinitrogen tetroxide is unreacted. And so that's what we're going to figure out now. The easiest way to figure out the amount of excess reactant is to look at the amount of dinitrogen tetroxide that will be consumed, right, with the reaction of hydrazine. And so to do that, we want to take the amount of hydrazine, 100 grams, we want to find the moles of hydrazine, and we want to make a relationship between the moles of hydrazine and the moles of dinitrogen tetroxide. So we can find out how many grams of dinitrogen tetroxide will be used in this reaction. Then we can subtract that amount from the initial mass, and that'll give us the excess. So in order to do that, we say we have 100 grams of hydrazine, right? And we did part of this before. Hydrazine is 32.05 grams for every 1 mole. For every 2 moles of hydrazine, there's 1 mole of dinitrogen tetroxide. And we want the grams of dinitrogen tetroxide, so we use the molar mass. So for every 1 mole of dinitrogen tetroxide, there are, 92.02 grams. So this equals 144 grams. All these cancel out. Okay, so this is how much dinitrogen tetroxide is going to be consumed in this reaction, right? This is how much will react with the hydrazine. So if we started off with 200 grams of dinitrogen tetroxide, and we use up 144. If we subtract these two numbers, then we'll get the amount that remain unreacted. So this is 56 grams of N2O4. So we found the limiting reactant, right, by finding the amount of moles of N2 that would be produced, right? And then we were able to calculate the grams of N2 that would form using this limiting reactant. And then we were able to figure out the amount of dinitrogen tetroxide that would get used up during this reaction and subtract it from the initial amount in order to get the excess mass.